All right, recording is rolling. It is Friday, November 4th. Long Friday, long Friday. So today's gonna be a really good day for to make up any work you need to make up. So you guys know I'm picking up from you guys chapter 10, 11 puzzles. That's these right here. We finished these in class yesterday, so as long as you follow along, you should be good to go on that front. Your guys' projectile spring constant lab and also the pendulum lab. Okay, so I'm picking this up today. Okay. And you know what? On the back side of this are all these conceptual questions. We never address these directly, but there are a few of your quiz questions on your open notes take-home quiz that's due Monday, right? That are directly on here. So we're about to run a Kahoot that covers all these questions and answers, okay? Right, so you guys know we're about to do a Kahoot that's going to answer some of these questions that are on your quiz that's due Monday, right? In fact, if you guys happen to knock out your quiz before you leave class today, which is good because it's a good opportunity to do that, then you won't have to worry about any of the stuff over the weekend, right? But if you guys got some spare time, I do have some Legos and board games out. You guys remember also today is picture makeup day in the gym lobby. So if you need to do a picture makeup, this class would be a pretty good opportunity, I think, to do that. And oh, I've got one more note squeezing here on the bottom. Daylight saving ends this weekend. So this weekend is 1 hour extra longer. Right, so you guys ready to do Kahoot? Let me switch my screen to share. All right. I got a few guys lined up. All right, got a bunch of guys logged on here. All right, we're about to get a bunch of quiz answers. Again, if you want to follow along, these questions are printed on the back side of those labs. All right, here we go. We're going to do a kind of a fast version of this so that you guys have enough time to, if you need some time in class to work on some stuff. All right, work. Work is defined as I think it's the first definition I gave you. Yeah, there you go. Force times distance, right? And that would be a transfer of energy. Force times distance. There you go. If you push twice the force for twice the distance, or if you lift a weight, twice the weight for twice the height, same idea. How many times the work? What's a factor of 2 times a factor of 2? 4 times, 4 times. All right. Got Tony Gunk in the lead. What's the unit for work? Which is the same thing as the unit for energy. Energy or work is measured in energy work. Yeah, joules, right? There's also calories and BTU and kilowatt hours, but yeah, joules what we most care about. Tony Gunk keeping the lead. Power. No, it's work divided by time. Oh, one winner, one winner. Yeah, guys, work divided by time. You guys know that power is like a rate of work. You could also say energy divided by time, right? Rate of energy, rate of work. Okay, guys, if you look on a light bulb and the light bulb says 40 watts and you plug it in, it turns on. 40 watts, isn't that like 40 joules per second? Right, like energy per time that's flowing off the grid. So the unit would be watt, wouldn't it? Power is measured in watts, which is joules per second. Right, that's a rate of energy, rate of work. Rifa on fire, but Tony's still in the lead. What is the unit for power? I'm about to find out who's not deaf. Oh yeah, watts, which is joules per second, right? Number stamped on light bulbs. Tony keeping the lead. The amount of potential energy possessed by an elevated object is equal to yeah, the work done lifting it. Oh, one winner again. All right, so guys, a couple of perspectives on this. the work you do lifting something, couldn't that be force times distance, like force times height, which is also mgh, and mgh is also potential energy. Okay. Another perspective is that this is the only one that the units even work out. Because guys, what's the units for work? Joule. What's the units for potential energy? Joules. What's the unit for power? Watts. The unit for force? Newton. The unit for distance? Meters. There's only one where the units even match. You guys catch that? Right. So the work you do lifting something is equal to the potential energy that it ends up with. Right? Okay. All right. Who got that? General Kenobi. Oh yeah. Kinetic energy is equal to one FMV squared. Oh, everybody. It's on fire. How much farther will a car traveling? Okay, so if you double the car speed, what happens to the braking distance? That's another way to say this. Double the car speed, what happens to the braking distance? Pretty sure I talked about this one a few times. So this was also in your guys remember that 3-page energy table? That's the fourth one we did. Yeah, 4 times as far. Because remember, the braking distance is proportional to the square of the initial speed. So there you go. Double the distance, you need 4 times the amount of road to come to a stop. Oh, General Kenobi taking top spot. And he's on fire. An arrow and a bow has 70 joules of potential energy, you know, like spring potential in the string. How much kinetic energy? Pew, when it's fired. If energy is conserved, yep, then 70 joules of kinetic energy. Suppose all the energy goes into its motion. That would be true, right? My tummy hurt, on fire, Tony in second, General Kenobi in first, as the pendulum swings back and forth. See, at the end points, it's all potential energy. At the lowest point, it's all kinetic. Kinetic and potential oscillate back and forth. Yeah, those are all true statements. All true statements. You guys did a whole pendulum lab. You guys did go on that one. Oh yeah. When a car's speed triples, what happens to its kinetic energy? 1/2 mv squared. Right, 1/2 mv squared. So 3 times the speed is 9 times the energy. Yeah. Of course, that would also translate to 9 times the braking distance. Slammed on the brakes. Talk about that one. All right, so you do 2 jobs, identical jobs, same amount of energy, but different amounts of. Okay, if you do different time intervals, you do different amounts of what? Same work, same energy. Wait, energy per unit time. Ooh, called power. Yeah, different amounts of power. So suppose you lift identical weights, identical heights, equal number of joules of energy lifting it. Right? But suppose you do one job in like 2 seconds, one job in 3 seconds. Well, if you divide by 2 seconds, you'll get some number of watts. If you divide by 3 seconds, you get a different number of watts, right? Joules per second, right? In fact, there's more watts to do it in less time, isn't there? Right? The faster you do the job, the more watts, right? The more power. General Kenobi, get the lead. Which requires more work, lifting 70 kilograms up 2 meters or half the weight up twice the distance? Has half the mass, it has half the weight, right? Let's get that. There you go. Everybody got it. Yeah, so the factor 2 and factor 1/2 cancel out. Yeah, same number of joules of work. An object that has kinetic energy must also have, well, must have a mass, must have a speed. Therefore, it must also have Yeah, okay. Momentum is what we're gonna start next week. Momentum, mass times velocity. Okay. Now it turns out the momentum is conserved to the universe a lot like energy is, but it's going to be a vector quantity instead of a scalar. All right. So you guys see it has like the same ingredients as kinetic energy, right? Mass, velocity. Now they're arranged differently. It's not 1/2 mv squared. It's mv, but same ingredients. A pulley system. Hey, you guys ready to get some pulley systems? Were you able to multiply your strength, multiply a force? Were you able to change the direction? Could you do both of those things? Could you increase the amount of energy in the universe? Yeah. All right. So the blue and the green, and the best answer would have been the gold one, but yeah, whatever. Right. But you can't increase the amount of energy in the universe. Right. Tony, back in the top spot. Andy's on fire. How many joules of work done pushing about 25 newtons for 3 meters? How much work? Work equals force times distance. Oh yeah, force times distance. How much power? 40 joules of work in 5 seconds. Say power is measured in watts, which is joules per second. If you take 40 joules and divide by 5 seconds, there you go. It's 8 watts. Yeah, that's 8 joules per second, 8 watts. How much work? 30 Newton crate lifting 2 meters.
Really like crate.
Yeah. True. Yeah, there you go. Great. There you go. At 60 joules, right? 30 newtons times 2 meters, force times distance, weight times height. There you go. How much power? Lifting 60 Newton crates, 10 meters, all in 2 seconds. Guys, what's 60 newtons times 10 meters? 600 joules. What's 600 joules divided by 2 seconds? 300 watts. Bam. Right? Force times distance over time. Be work over time, which is power. 300 watts. For the win. For the win. A machine puts out 200 watts of power for every 1,000 watts input. What's the efficiency? Because this is just a continual process. What is 200 divided by 1,000? 20%. 20%. There you go. It's a decimal. It's called 0.20. 20%. To the podium with the bronze, Tony. With the silver, General Kenobi. Ooh, who got the gold? Snadson. Oh yeah. Got Ade and Matame. All right, nice job, guys. Nice job. Okay, so you guys got rest of class. Make the best use of this time. You guys remember these things are due, but you probably have those finished already. You can work on your energy quiz if you want to. Got Legos and board games for you guys. All right, and that is a wrap on this recording.